All right, g'day and welcome to the third video for topic 3 for week 9. So we're looking at some questions relating to the kinetic theory of gas. So in this lecture we've talked about the idea of gases as being a whole bunch of moving particles and temperature being a representation of the kinetic energy of those particles. And we talked about some of the assumptions of the ideal gas model. So now we've got a few questions, just 3 today, 3 that I've come up with for kinetic theory of gases. So we'll jump straight into the questions. It is a nice sunny day and the air outside is at around 28 degrees Celsius. The air is made up mostly of nitrogen molecules with a mass of 28.02 U, and oxygen molecules with a mass of 31.98 U. What is the RMS speed of the nitrogen and oxygen molecules in the air? As usual, I really just want to reinforce that you should be attempting these questions yourselves. Don't just watch this video and go, yeah, I can do that. Actually try it. That's the only way to be sure. So with that said, that should have given you enough time to pause the video, have a go at the question, and now we'll have a look at a solution. So the information we've been given is that temperature is 28 degrees C. We have 2 different scenarios. We've got mass of nitrogen molecules was 28.02 U, and the mass of the O2 molecules was 31.98 U. We're looking for V RMS for both of them. All right, so we'll get 2 different values because we've got 2 different masses. Remember that if they're at the same temperature, that tells us that the kinetic energy of each particle is the same. But of course, the average kinetic energy is going to be different because we've got different masses. Sorry, the average kinetic energy is the same, tells us the velocity is going to be different because we've got different masses. So that's the first thing that we do. We write out what we know. But when we're thinking about this sort of problem, it's always good to have some idea of what we expect. Now, I've just said that we expect them to be different velocities because they've got different masses. So it would be useful at this point to think which one do we expect to be bigger? Because even just something as simple as that, as simple as saying, oh, I expect which one of these to have a higher velocity. When we get to the end and we've got our numbers, we can say, that thing that I expected right back at the start before I did any calculations, is that true? Is that correct? And if it is, then it doesn't guarantee you are correct, but at least it means that you know you're not definitely incorrect, if that makes sense, right? So it's just useful to have a little check like that. Okay, so first thing is thinking about what sort of equations we're going to need. Now this one is actually just given straight to us. VRMS, I'll switch colors. VRMS is equal to the square root of 3kT over m. That's the formula that's given to us that we found through the kinetic theory of gases by considering just the kinetic energies and looking at the pressure and relating that to the ideal gas law. We got this equation. VRMS is equal to this. So that's fine. 3 is just a constant, a number. K is a constant, Boltzmann's constant. T is the temperature, and we've been given the temperature, and m is the mass, and we've been given the 2 masses. So it's just a matter of using that equation twice, once for each particle. But of course, we do need to think about the units. This needs to be a temperature in Kelvin. It's an actual reading of a temperature. Right? It's an actual reading, not an interval, not a step in temperature. It's an actual temperature. So we need to convert this into Kelvin. And of course, that is just plus 273 to 1, to the nearest whole 1. So we add on 273, and that will give us 301, won't it? 301 Kelvin. Right? So we've got 301 K. Then we've got 2 different masses to calculate. We have to remember what U is. 1 U, 1 atomic mass unit. You'll always be given this in test type scenarios, or you can Google it or look up references if you're at home working on your own. But it is 1 U is equal to 1.66 times 10 to the minus 27 kilograms. That's all it is. So for both of those, we just need to times that number by this, That'll give us a mass in kilograms. Same for that one here. So let's do that. Let's have a go at these. We've got the nitrogen mass. Mass of nitrogen is 28.02 times 1.66 times 10 to the minus 27. And that should, if you've got your calculator and have a go at that, it should come out to 4.65 times 10 to the minus 26 kilograms. So there's our nitrogen mass. And then we've got the oxygen mass. It's exactly the same, but we've now got 31.98 U instead of 28.02. 1.66 times 10 to the minus 27. And that will give us, again, please do these calculations. Don't rely on me. I do make mistakes. And you're not going to get the same practice if you just watch. Have a go at them. So those are our two masses. Now in kilograms, we've got the temperature in Kelvin, the masses in kilograms, and that's all we need. We do need to know what K is. You can look up K. K is simply 1.38 times 10 to the negative 23. It will have units, but I'm just worried about the numerical value now. So if you're doing that sort of calculation, you should include the units. So when you look it up, get the units as well. So now we can do our actual calculation. V RMS for nitrogen is equal to the square root of 3 times 1.38 times 10 to the negative 23 times 301 Kelvin, all divided by the mass of nitrogen, our molecule, which is 4.65 times 10 to the negative 26 kilograms. And that will give us a speed. Right, and our speed should come out to be 518 meters per second. All right, 518 meters per second for that one. And same calculation, but for oxygen. I'm not going to write out the whole term, but if you do that one, you should hopefully get 484 meters per second. Now the value, the temperature value was only given to us in 2SF, but the masses were given to us in 4SF. So there's, I've written my answers to 3SF, but you'd be perfectly valid rounding to 2 significant figures based on the temperature that we were given being only 2 significant figures. So that is that question, right? Nothing too difficult there. Pretty straightforward calculation, but a reminder that you do need to use SI units. As you can see, slides have the same answers written out in there. Next question. We just saw that for oxygen, an oxygen molecule, O2, on a warm day, the RMS speed is 484 meters per second. And actually, while I remember, you should be double checking that your first thought about the system was correct. When I said, think about which one of these molecules you expect to have a higher velocity, you should have hopefully thought nitrogen would, because it's got the smaller mass. If you've got the same kinetic energy, smaller mass should be nitrogen. So hopefully your first thought was nitrogen should have a higher velocity. And then when you get to the end, you can go, hey, look, nitrogen's slightly bigger than oxygen. So it's only worth making those little thoughts at the start if you remember to check them again at the end and actually make sure everything's in agreement. So we saw that the VRMS for oxygen on a 28°C day was 484 meters per second. Right, that's very quick. It is 1,740 kilometers per hour, in fact. And so very high speeds. And the question now is using the Maxwell distribution of speed. So remember that big messy function that we're going to play with. We are trying to calculate how many oxygen molecules would have a speed between 2,000 kilometers an hour and 2,100 kilometers per hour. And we want to show this as a percentage of O2 molecules, right? So we've got a couple of steps here. First is to use the distribution of speed to figure out the number of molecules traveling in that range, given our number of molecules is 1 mole. And then we want to convert it to a percentage so that it would be true for any amount of gas at, any amount of air at 28°C. So there's a bit to do on this one. And of course, probably the most daunting part of this is the fact that we're going to have to use Maxwell's distribution of speed. And if you recall from these slides, that is not necessarily a pretty one. Oops, I just showed you the answers. But anyway, we'll go back to here, Maxwell distribution of speeds. That is our formula that we're going to be using. It's a big, messy one. Well, it's not messy, it's just got a lot of terms in it. They are all terms we know everything in here, but there are quite a few things to calculate. So it is easy to make mistakes. So just a bit of extra care is warranted is my point, I guess. Let's go to the document camera and we'll have a go at this. So first thing first, let's write out that Maxwell's distribution of speeds because we're going to be dealing with that. So f of v is equal to 4 pi n times m over 2 pi kt, and that's all to the power of 3 over 2. Then we've got the velocity squared. Then we've got the exponential of -1/2 times mv squared over kt. Right. So that's our function. We now have to go through and figure out what all of these values are that we're looking for. So remember that the graph, when we graph that, we have velocity and we have f of v. And we said that that'll always end up looking something like this. It starts at 0. It'll have a peak at some point, which will be a bit below VRMS. So RMS won't be where the peak is. The peak will be a bit below it. But that'll be the peak. It'll go down to 0 there, and then it'll go off to infinity, approaching very small values up there. I didn't draw that quite too well, but you get the idea. That should really be a bit curvier than that. So that's what we've got, and what we've been asked is how many molecules are there between two certain temperatures. Now we found out that the VRMS for oxygen was 1,740, I think it was, kilometers an hour. That was there. And what we've been asked now is to find out how many molecules are between 2,000 and 2,100 kilometers an hour. So that means we have to find the area under the graph. That's what we're looking for. We're looking for the area under the graph between 2,000 and 2,100. Now, if you recall the example in the slides, we said one way to solve this. If you zoom in on that, it's going to look something like this, right? It's going to look something like that. Because it's only a small portion of a curve, we can treat this as being almost a straight line. It's very close to being a straight line, and for our purposes, that'll be good enough. So if this is the number f of v at 2,100, other way around, 2,100 there, 2,000 there, what we can do is find instead the value halfway, right, at 2,050, and then we can just do a rectangle. So we use that as our height, and we use the difference from 2,000 to 2,100 as our width, and then we find this whole area here. And that'll be the same as the area would be if we found it for the actual area under the graph, because what we're saying is that this little bit here is about equal to this little bit here. Right, so we're calculating this bit extra, but we're calculating this much less, so we should be calculating a pretty close estimate for our value. And so that's the process that we're going to do. So all we actually have to do is use this equation once, and we have to use that equation for the speed 20,050. Now remember, that's in kilometers an hour. So what we're going to do is we're going to write out our three speeds. We've got V, I'll call them V left is equal to 2,000 kilometers an hour, and we want to convert that into meters per second. So you all should remember how to do meters per second from that. Times it by 1,000 will turn it into meters, and then divide it by 60 twice will turn it into minutes and then seconds. So to get meters per second, we multiply by 1,000, divide by 60 squared, and that comes out to be 555.6 meters per second. I'm not going to round it to only a couple of SF yet because we're still doing some calculations. So I'll keep it to 4 SF for now. Realistically, you should probably keep a few more significant figures, but since I'm writing big numbers to try and make it visible on the camera, I'm just going to write 4 SF for now. And so same thing for the right-hand side, the other end. So we had V left and V right. We've done that one. We do this end. This is 2,100 kilometers an hour, and that comes out to be 583.3 meters per second. And now what we're going to do is get that central value, right? This central VC, which was our 2050, halfway in between, because that'll give us the height of this rectangle we're looking for. So VC is equal to 2,050 kilometers an hour. And so doing the same calculation to that, we get 569.4 meters per second. So we have to figure out the Maxwell distribution of speed function result for, I've written that wrong, for 569.4. So when V is equal to 569.4, what does F of V equal? That's our goal. So we've got everything set up now. So once we know this, that tells us the height of the function at that point. And since we want the area, we need the height of the function, which is going to be that, times the width, the difference between VL and VR, and we've just calculated them. So these will give us the width is equal to the difference between these two, right? So the difference between those two is, I don't know if I've actually written that down for myself anywhere. I will get my calculator and we will calculate it. The difference between those two is 583.3 minus 555.6 is 27.7 meters per second. So that's the width of our gap, the width of our block that we're trying to find the area for. Now we just have to find the height. So that is this function here, right? But now with our new velocity, which I'm just going to write up the top for reference, VC was equal to 569.4. So that's what we're doing. We're figuring that out for that. Now we need to remember what K was. We need to remember what M was. We need to remember what N was and T. We need to know all of those. So let's remind ourselves what they are. We were told it's 28 degrees Celsius, which we saw before was 301 Kelvin. We also found that the mass of an oxygen molecule, if you remember we did that one already, mass of an oxygen molecule was here, 5.31 times 10 to the negative 26 kilograms. 5.31 times 10 to the negative 26 kilograms. We already saw K as well, which is 1.38 times 10 to the negative 23. And I really should get the units for that, but I always forget them. You can find them up. That's a task for you guys. Find the units for K. Just because I've forgotten, we could just go back a slide and find them. But anyway, we've got K. We've got N is equal to 1 mole, which is 6.02 times 10 to 23 molecules. I did that one from memory, so hopefully that's correct. And we've got, what else do we need? 4 pi n, m, k, t, v, we've just said e, m, v squared, k, and t. So that's everything. That's all we need for this function. So now we can actually solve the function. Right. So a function of 569.4 is equal to 4 pi times 6.02 times 10 to the 23 times, in brackets, 5.31 times 10 to the negative 26 all over 2 pi times 1.38 times 10 to the negative 23 times 301. That's on the bottom of that fraction. All of that times v squared, which is 569.4 squared. Oh, that whole bracket, sorry, is to the power of 3 over 2 times velocity squared times the exponential of minus a half times we've got the mass, 5.31 times 10 to the negative 26, times the velocity squared, 569.4 squared, all over k, 1.38 times 10 to the negative 23, times the temperature again. That's all in that exponent. Okay. So it's a lot to calculate. If you try and type that in your calculator, you might even find that it won't let you type all of that in at once, right? It's too long for it. So when you're dealing with calculations of this size, there are a few ways to go about it. One is you could go online, go onto your computer and use a spreadsheet, or use Wolfram Alpha or some kind of online tool. If you're familiar with programming, you can write a little, just write it up in programming language or something. So there's a few ways to deal with it. If you are stuck doing it with a calculator manually, what I recommend, my personal approach, is to break it into separate terms. So what I would do is I would do this, and I'd call this term A, or 1, or whatever you want. I'd call this whole bracket to the power of 3 over 2 term B. I'd call this V squared term C, and I'd call this exponential term D. And so now I know that it's equal to A times B times C times D. And then I'd go and calculate each of them individually. So I'd end up saying that it's whatever 4 pi times this is. I'd get that number, and I'd write that in. And then I'd do evaluate this thing. So a fraction, do that fraction, and then take the fraction to the power 3 over 2, write that in. And so I'd fill in those 4 blanks for each of those terms. Then I'd multiply all of them out. And hopefully, if you all have had a go at that yourselves, if you get that out, you should hopefully get, I don't remember where I have done this calculation for myself. So I will write out my answer. 2.48. So I get, I think I got 8.953 times 10 to the 20. I think that was my result. I've made quite a lot of notes here, so hopefully that's correct. Feel free to correct me if you get something different, or go and ask in the forums. We'll see if we can make sure we've all got the same value. And so then what we're looking for, remember, was the number of molecules. Right? So the number of molecules where the velocity is between 2,000 kilometers an hour and 2,100 kilometers an hour. And we said that that is going to come out to be this area. So that value we just found, this 8.953 times 10 to the 20, that's the height here. And now we've got to multiply it by the width, which we said was the difference in the two velocities. So that will give us the area. So it is equal to this number, right? That number times 27.7, which for me comes out to be 2.48 times 10 to the 22. So that's how many molecules there will be. So for oxygen molecules, between 2,000 and 2,100 kilometers an hour, there are 2.48 times 10 to 20 molecules, given we had 1 mole of gas to start with. So that's the first part and hardest part of the question. The next one is just to show this as a percentage, and that as a percentage is just going to be this divided by the number of molecules, which is 1 mole. So it equals that number, 2.48 times 10 to the 22 divided by 6.02 times 10 to the 23, right, 1 mole. And that comes out to be 4.13%. So slightly over 4% of oxygen molecules are traveling between 2,000 and 2,100 kilometers per hour when the temperature is 28 degrees Celsius, right? Over 4%. And just for interest, I'll jump back to the slideshow now. What I've done an extra little note there because I did some more calculations on that. And it turns out that almost 30% of molecules, oxygen molecules, in 28 degrees Celsius here are traveling over 2,000 kilometers an hour. So that number we said over 4%, that's just between 2,000 and 2,100. But there will be molecules faster than 2,100 as well. And it turns out that over almost 30% of them are traveling over 2,000 kilometers an hour. So very fast, but obviously they're so tiny that the force they impart, the impulse we get from them bouncing off us, is actually not that great. And but of course, that is where atmospheric pressure comes from, the nitrogen and oxygen and all the other gases in the air, all the other particles bouncing into us constantly at these high speeds. And the last question, helium gas is the closest real gas to acting like an ideal gas. So it's just a statement, there's no question there, but one of the mastery test or workshop questions, I think it was mastery test questions, was about why helium gas is a good example of an ideal gas, something like an ideal gas. So again, we've got 1 mole. We're just taking 1 mole as our number of molecules, and we've got 21 degrees Celsius this time. And the question is asking us, what is the internal energy of that sample of gas? Then the next part of the question is that if the internal energy doubles, what is the temperature now? So two steps to this question. But the first one should be fairly obvious and fairly straightforward. Nope. There we go. All right, so we'll jump over to the document camera and we'll have a go at this one. So we've got helium gas, which, as we've said, is pretty much an ideal gas. So that simplifies it quite a lot. What it means is that for an ideal gas, the internal energy is equal to the sum of all the kinetic energies, right? So all the kinetic energy of all the little particles becomes the internal energy. Because remember, internal energy is all of the different types of energy in the system. But for an ideal gas, we're saying there's no other kind of energy it can have. It's only kinetic. So therefore, if we can figure out the kinetic energy of each particle and add them all up, then we can get the total internal energy. Of course, we can't actually measure the kinetic energy of each particle, but we know that the average kinetic energy is equal to 3/2 kT. So therefore, if we've got n particles, then n times k will be our total kinetic energy, and that will be our internal energy, right, which is going to be 3/2 nkt. So that's all we have to do, that calculation. We've been told that n is equal to 1 mole, which equals 6.02 times 10 to the 23. We've been told that, we already know k. K is what we saw multiple times before. And actually, at this point, we can stick with k. But you will see that you can also do it as, remember the other format, nk is actually equal to nr. And n would then be 1, and r would be the universal gas constant. So you could switch to that format if you wanted. I'll stick with k for this time, but you can certainly do it that way. 1.38 times 10 to the minus 23. And temperature, we've been told 21 degrees Celsius, which we have to add 273 on, is going to be 294 Kelvin. Right, so 294 Kelvin, then we've got those two values for K and N, and we've got 3/2 out the front. Hopefully, if you multiply all of that together, you'll get out 3,700 joules. Right, or if you want to switch, 3.7 kilojoules. That is the internal energy of our helium gas 1 mole sample at 21 degrees Celsius. The next part of the question said that we now have the internal energy is doubled. All right, what happens to T? Well, if you look at this equation here, we're keeping N. I'll write it out again. E internal is equal to 3/2 nkt. So N is not changing. That's not changing. This can't change. That can't change. Those are all constants for this scenario. Well, K and 3/2 are always constants. N is constant for this scenario. What we're saying is this goes up 2 times. If this side of the equation doubles, this side must double. So T must go up 2 times as well. So that means that we have a temperature which is now doubled. The new temperature, T prime, we can stick with prime notation. You should be familiar with that, possibly. But the new temperature is now going to be 294 times 2. Because remember, we've got to stick with kelvins. All right, we've got to stick with Kelvin for our temperature since we're talking about actual temperatures, not differences. 294 Kelvin becomes doubled, which becomes 588 Kelvin. Or if you want to switch back into degrees C, take off 273 again, we end up with 315 degrees C. So 315 degrees Celsius would be double the internal energy of 21 degrees Celsius. So that question, the reason for having that little doubling question in there is just, it's quite fascinating because people don't often think of how much energy it takes to get from absolute zero up to 21 degrees C, because to us 21 degrees C just seems like a nice, peaceful, comfortable temperature. But the amount of energy it took to go from absolute zero up to 21, up to our standard room temperature, that much energy again would take it all the way up to 315 degrees Celsius, right? So that's how much energy it took to get to where we are from absolute zero, which is just a fascinating little bit of information. So that brings us to the end of the questions for topic 3, which is the end of topic 3, week 9 in general. So that's the end of these videos for week 9. You'll see me again with next week's videos where we'll move on to some new topics.